Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to the course of Algebraic Topology. My name is Suhail Iqbal. I'll be your instructor throughout this course. So these are the textbook for the course. Mainly we will be following Joseph Rotman's book, An Introduction to Algebraic Topology. So side by side we will also be looking at the book by Alan Hatcher, namely Algebraic Topology. So these are our additional books. BK Larry, it's a simple book, a first course in algebraic topology. And if you are interested in the algebraic topology of manifolds, then we have another additional book called Lectures on Algebraic Topology by A. Dold. So this is going to be your marking scheme throughout this course. For quizzes we have 10%, for assignments we have 10%, and for GDBs we have 5%. Sessionals will be marked and their weightage will be 25%. The final will be 50% weightage. So what is algebraic topology? So as the name suggests, that it has something to do with algebra and topology. So mainly we are connecting them, but as the history suggests that mathematicians started using algebra to study topological objects. So in particular they use groups. So they associated groups with topological objects, and then they study topological properties using properties of the groups. But this is not just a one-way stream, it's a two-way stream. So sometimes we can prove very complicated results of algebra, especially for groups, using this bridge of algebraic topology. So there are many applications of algebraic topology. For example, if you are interested to see the solvability of differential equation defined over a manifold, then for this purpose we need to calculate some appropriate cohomology. So what is a cohomology? These are some sort of groups that we need to calculate. And there are also applications, for example, in fixed point theory. So to prove Brouwer fixed point theorem, which states that if K is a convex compact subset of an Euclidean space, then every continuous function has a fixed point. So to prove this theorem, we can also use algebraic topology. So there are many other proofs as well of this theorem. We can also use homotopy groups to classify topological spaces, and we can study manifolds in general, and we can also study properties of groups using algebraic topology. So here's our lecture 1 plan. So we will review some previous concepts, so starting from what is a set, and then we will review what is a group, and then going to vector spaces and linear transformation. Our main emphasis will be on the concept of group because we will be using it very frequently in our subsequent lectures. What is a set? So when the word set come in our mind, then it means a collection. So we need to define a collection. So when mathematicians need to use some idea or notion, then of course we need to define it very precisely. So roughly speaking, a set is a collection of well-defined distinct objects. But when a mathematician wants to use it, then of course he or she needs to define it precisely. Then there are many definitions, but the one by the theory of ZFC is the most common nowadays. And we are not going to the definition according to this theory, but it's just a reference. If you are interested, then you can look it into some book. What is a subset? A subset is, so A is a subset of B if every element of A is also an element of B. So for example, if A is equal to 1, 2, 3 and the set B is equal to -1, -2, 0, 1, 2, 3, 4, then every element of A is also an element of B. So A has an element 1, which is also an element of B. A has an element 2, which is also an element of B, and A has the third element 3, which is also an element of B. So we can say that A is a subset of B. So we will differentiate between the set and the term class. So as I said earlier, that sets are precisely defined using many theories, but the most common nowadays is ZFC, and we are not going into the details of the definition, but the point is there is a difference between the word set and the class. So class is basically some sort of very big collection of objects. So such a big collection of objects that the definition of set can't cover this collection. So for example, a collection of all sets is not a set, so it's a class. So similarly, we can say that collection of all topological spaces is not going to be a set, and it's going to be a class. Collection of all groups, collection of all compact topological spaces, collection of all Hausdorff topological spaces, collection of all abelian groups. Similarly, there are many other examples which are classes but not sets. So once again, what is a set? That satisfies some certain axioms. So for example, given by the theory of ZFC. Cartesian product. So the Cartesian product of two sets A and B, denoted by A cross B, is defined as the set of ordered pairs A into B, where A belongs to capital A and B belongs to capital B. So in other words, it's the collection of all ordered pairs where the first element or the first coordinate belongs to A and the second coordinate belongs to B. So for example, if my set A is equal to Z into Y and set B is equal to 1, 2, 3, then A cross B is set of all ordered pairs, set of all possible ordered pairs, such that we have the first coordinate to be element of A and the second coordinate to be an element of B. So for example, in this case, Z1, Z2, Z3. So in all of these ordered pairs, the first element belongs to A and the second element belongs to B. Similarly, Y1, Y2, Y3, in these ordered pairs, the first element belongs to A and is Y, and the second element belongs to B. So we can see that this is the all possible ordered pairs with the first element to be an element of A and second element to be an element of B. Similarly, we can define Cartesian product of other sets as well. A relation. So a relation on a set A is a subset R tilde of A cross A, and we write A related to B if the ordered pair AB belongs to R tilde. So for example, if I have a set A to be 1, 2, 3, then what is A cross A? So the set A cross A is basically collection of all ordered pairs 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So as we can see that this is the set of all possible ordered pairs with first element belongs to A and the second one element also belongs to A. So that's how we define A cross A. So now take any subset of A cross A. So for example, if I take R tilde to be 1, 1, 2, 3, and 3, 1. So as we can see that R tilde is subset of A cross A because it has three elements 1, 1, 2, 3, and 3, 1. And these three elements are also elements of A cross A. So R tilde is subset of A cross A. So this R tilde, by this definition of relation, is basically a relation on A. Now what is an equivalence relation? A relation is said to be equivalence relation if it satisfies the following condition. So A must be related to A. So in other words, we are requiring that it must contain A. Secondly, if A is related to B, then B is related to A. So in other words, if AB belongs to the relation, then this implies BA is also an element of the relation. Similarly, if AB belongs to the relation and BC belongs to the relation, then this implies AC also belongs to the relation. So if a relation satisfies these properties, then this is an equivalence relation. So let's try to find an example of equivalence relation on this set A. So of course equivalence relation is a relation, so it has to be subset of A cross A. So let's try to find out a subset R tilde prime of A cross A which satisfies all these three conditions. So the first condition of reflexiveness shows that it has to contain AA for every A belongs to A. So in other words, it must contain 1 1, 2 2 and 3 3. And the second condition imposes that if AB belongs to the relation, then BA must also belong to the relation. So of course 1 1 belongs to R tilde dash, then of course it's symmetric, 1 1 also is in this set, and similarly for 2 2 and similarly for 2 3. But if I add one more element, let's say 1 2, then 2 1 must also be in this set due to this symmetric property. Let's go to the property number 3. So the property number 3 requires that if AB belongs to the relation, BC belongs to the relation, then their composition kind of ordered pair, that is, if I ignore this B in between them, then AC belongs to this relation as well. So in this set, let's see if we need to add another ordered pair or not. So all the composition, we can see that all the composition are also in this set. So for example, the composition of 1 1 and 1 2 is basically 1 2, which is also in this set. Similarly, the composition of 2 1 and 2 2 is also in this set, which is namely 2 1. So similarly, other composition also belongs to the set. So this R tilde prime satisfies all these three properties of equivalence relation. Okay, so this relation, which is a subset of A cross A, is an equivalence relation. So what is the main purpose of the equivalence relation? So if I define an equivalence relation on a set A, then basically it divides the set A into classes, and each class is basically, and if I take union of these classes, then I will get the set A. So it's basically a way of writing down a set A as a disjoint union of classes. So we will see that this equivalence relation is used in many places during the course of our lectures. So the equivalence class of an element A is denoted by this. So square brackets A, and this is basically equal to set of all elements B belongs to A such that A is related to B. Let's go back to our example and see what is the equivalence class of, for example, 1. So the equivalence class of 1, set of all elements which are related to 1. So 1 is of course related to 1, so 1 is going to be part of this equivalence class. And there is another element which is related to 1, that is number 2. So the equivalence class of 1 is 1 2. Similarly, we can calculate the equivalence class of 2. So as we can see that 2 is related to 2 due to this ordered pair, so 2 is going to be part of this. Similarly, 2 is also related to 1 due to this ordered pair, so 1 is also going to be of this set. Similarly, we can calculate what is equivalence class of 3. So 3 is basically only related to 3, so the only element in this equivalence class is 3 only. So we can see that there are two different equivalence classes. So one equivalence class of 1 is equal to the equivalence class of 2, because equivalence class of 1 has two elements 1 2, and equivalence class of 2 has two elements 1 2, and they are equal. So basically it's just one equivalence class. So we can denote it by 1 or 2, whatever you like. Similarly, we have another equivalence class denoted by 3. And as we can see that the intersection of the equivalence class of 1 and the equivalence class of 3 is empty. So there is no element in their intersection, there is no common element between them. Also, if I take union of 1 with the equivalence class of 3, then this is exactly equal to 1 2 3, which is the set A. So as I said earlier, one use of equivalence relation is to divide A into disjoint union of classes. So in this example, we have divided this set A into disjoint union of two classes. Let's start with the concept of groups now. So the first definition that we need to study the concept of group is the concept of binary operation. So what is a binary operation? It's just a function from A cross A to A, and usually we denote it by x star y. So for example, if my set A is set of real numbers, then addition is a binary operation on set of real numbers. So if I have two real numbers, for example 2, then I can add it to another real number and I will always get a real number. Similarly, if I have in general any two real numbers, then their addition will always be a real number. So it's a function from R cross R to R, so it is a binary operation. Similarly, multiplication on the set of real numbers is also a binary operation. So if I multiply any two real numbers, then I will always get a real number. So we can also say that multiplication is closed in set of real numbers, or addition is closed in set of real numbers. So what is a group? A group is a set with a binary operation satisfying the following condition. So the number one condition is also called associative law. So the associative law says that if I need to multiply three elements of a group, then I can multiply them in any order. So if I multiply first two elements and then multiply the result with the third element, or if I multiply the last two elements and then multiply the result with the first element, then there will be no difference in the result. So this is also called associative law. So according to this law, I can write down multiplications to be G1, G2, G3 without the use of brackets. So I don't need brackets because I can multiply the elements in any order and there will be no change in the result. So that's one of the usage of the associative law. The next condition that this set needs to satisfy is that there exists a unique element E. So this element E is called the identity element. So this axiom is also called existence of the identity. So this element E must satisfy the following condition, that if I multiply any element of the group G with E in any order, then there will be no change and the result will always be G. The last condition is that for every element G there exists an element G prime such that G into G prime is equal to G prime into G is an identity element. So of course we are using the identity in the last axiom, so we need to confirm that there exists identity element in the group before going to the last axiom. So let's see examples. So as we have seen that set of real numbers is closed under addition, so R under addition. So let's see if R under addition is a group or not. Of course I can add any three real numbers in any order and the result will be the same. So for example, I can add x plus y first plus z and the result is the same as x plus y plus z. So in other words, associative law holds, or this set R under addition satisfy the associative law. Let's see if there exists an element such that if I add a real number in that element in any order, then the result is the same real number. So as we can guess that such a real number is 0. So if I add any real number into 0 in any order, then there will be no change of result in the element. Okay, so this 0 is identity. So number 3. So we need to check that for every element G there exists an element G prime such that if I add G into G prime in any order, then the result is my identity element. So in other words, the result should be 0. So given any real number, can we find a real number such that if I add that real number into X, then the result is 0? Of course that number is minus X, because if X is a real number, then minus X is also a real number. So if I add X into minus X, then this is going to be my identity element, and if I add them in any order, then the result is same. So that's why there exists element X prime, so in this case it is minus X. So if I add X into X prime in any order, result is 0. So all these axioms are satisfied by R under addition. So R under addition is a group. Similarly, we can find other examples as well. So what is a commutative group? A group G which satisfies the commutative property. So what is commutative property? G1 into G2 is equal to G2 into G1. So this group is also called abelian group. So set of real numbers under addition is a group, and if I add any two real numbers x plus y, then as we know that the result is the same as y plus x. So this group under this binary operation satisfies this commutative property. So we can say that R under addition is an abelian group. So there are many examples of groups which are not abelian. So for example, if we consider set of all invertible matrices with entries from set of real numbers, so this forms a group under the matrix multiplication. So this is an exercise for you, but the important property is that this does not satisfy the commutative property. So if I multiply two matrices A into B of order 2 cross 2 with entries from R, then in general A into B is not equal to B into A. So take any two matrices in particular, and this is an exercise for you to show that A into B is not equal to B into A. So what is a trivial group? A group with only one element, that is E, is called the trivial group. So for example, the group containing only 0 element is a trivial group. Similarly, a group containing only the identity, the multiplicative identity, is also the trivial group. And similarly, we can also define a group containing only the matrix identity is also a trivial group. So what is a subgroup? A subset H of a group G is called a subgroup of G if it is a group under the same binary operation. So the important point is H should be a subset of G, and it should be grouped under the same binary operation. So the binary operation of H and G should be the same. So for example, we know that R under addition is a group. So now let's consider set of integers under addition. So we can observe that if I add any two integers, then the result is also an integer. So addition is binary operation on Z. Similarly, we can see that it's also satisfying associative law. So associative law means if I add three integers in any order, then there will be no change in the result. So the next part is 0. So the existence of identity element. So 0 belongs to Z, which serves as an identity element. In other words, if I add any integer into X in any order, then the result is X. And for any integer X, we also know that minus X is also an integer. So for any X, there exists an element minus X such that their addition is 0, and we can add them in any order and the result will still be 0. So Z under addition is a group, R under addition is a group. We also observe that every integer is a real number as well. So Z is subset of R, and they have the same binary operation of addition. So it satisfies the definition of subgroup. So Z under addition is subgroup of R under addition. So let's go to our next definition. What is a left coset of H by an element G belongs to capital G is defined as, so G into H is equal to A into H, where H belongs to capital H. So basically you take an element of capital G and multiply it with the whole subgroup H, then we get this subset of G, and this subset is called a left coset of H by an element G. Similarly, we can define the right coset. Of course, we can guess that in the right coset we have H into G, and the elements will look like H, G, such that H belongs to capital H. So this is not A, in fact this is G. So in general, the collection of all left or right cosets does not form a group, and there are conditions under which this collection of all left cosets or right cosets form a group structure. So that condition is called normal subgroup. A subgroup H of a group G is a normal subgroup of G if G inverse is equal to H for all G belongs to G. So in other words, we can also say that G into H is the same as H into G. So if I multiply G on both sides, then I will get this condition. So it is the same condition as this condition for all G belongs to capital G. So next definition is the quotient group. So if G is a group and N is a normal subgroup of G, then the collection of all left cosets of N forms a group denoted by G quotient N, and this G quotient N is the collection of all left cosets of N into G. Cyclic group. So a very simple class of groups. So a group is cyclic if there exists an element G belongs to G such that every element in G is a power of G. So in this case, G is called the generator of the group, and the order of the group is the order of the generator. So we denote a cyclic group of order n by Cn or Zn. Later we shall see that other examples of groups generated by elements. Okay. So for example, if I take iota, so basically iota is equal to square root of -1. So if I keep writing down the powers of iota, so iota square is -1, iota cube, so iota cube is minus iota, and then iota raised to power 4 is 1, and iota raised to power 5 is once again one of these 4 elements, and every other power of iota is one of these 4 elements. So we can say that this is a cyclic group generated by iota. So in this case we can see that every element is power of iota. So this is iota raised to power 1, so this is iota raised to power 2, this is iota raised to power 3, this is iota raised to power 4. So this is basically a group with 4 elements. So it is cyclic group of order 4 generated by this element iota. So as I said earlier, later we shall see other examples of groups generated by elements, not just by one element but many elements. So a cyclic group of order 4 is given as 1a square a cube such that a raised to power 4 is equal to 1, as we have seen earlier that if I take a to be iota, then this generates a cyclic group of order 4, and it also satisfies this condition that iota raised to power 4 is equal to 1. So this is called a cyclic group because we have a cycle of elements. So starting from 1 we get a, starting from a we get a square, a cube, and then we end this cycle once again at 1. So it is a cyclic permutation or cyclic combination of elements, so that's why it's called cyclic group. Order of an element. So an element G of a group has an order n if a raised to power n is equal to identity, where n is the smallest positive integer with this property. If there is no such positive integer, then G is said to have infinite order. So for example, consider R under addition. So if I take an element 2, so is there exist any positive integer such that 2 raised to power n is equal to identity? So of course there is nothing like this. So basically this element 2 has infinite order. So 2 has infinite order. So on the other hand, if we consider this cyclic group generated by iota with elements iota minus 1 minus iota 1, then if I take an element, let's say minus 1, belonging to this group C4, then we can see that there exists a positive integer minus 1 raised to power 2 such that minus 1 raised to power 2 is equal to 1, which is the identity element. So there is this condition of smallest positive integer, so we can also observe that minus 1 raised to power 4 is also an identity. Similarly, minus 1 raised to power 10 is also an identity. So what is the smallest of all these positive integers? Of course, that smallest positive integer is 2. So that's why this 2 is the order of element minus 1. So minus 1 has order 2. So an important concept when we are discussing groups is homomorphism. So a map phi of a group G into a group G prime is homomorphism if phi of A star B is equal to phi of A circle phi of B. So this star is basically binary operation of G, because A and B are elements of G, so we are operating A and B using the binary operation of G, and this circle, small circle, is basically binary operation of G prime, because phi of A is element of G prime and phi of B is also an element of G prime, so we are operating them using the binary operation of G prime. So let's consider a map, a function phi from GL to R under multiplication. So this means that set of real numbers under multiplication and there exists no zero element. So we are excluding 0 when we are considering set of real number under multiplication, because 0 does not have a multiplicative inverse. So that's why we exclude this 0 from this set to form or to make it into a group. So this set, which is set of all real numbers but the 0 element, forms group under multiplication. So let's consider this function phi. So phi of m is equal to determinant of m. Of course we can calculate determinants of 2 cross 2 matrices. So if I have a matrix 1 1 a1 2 a2 1 a2 2, then I can calculate its determinant. So determinant of this matrix, is a1 1 a2 2 minus a1 2 a2 1. So this function phi, which is from the set of all invertible 2 cross 2 matrices with entries from set of real numbers to R under multiplication non-zero real numbers, is a function defined by this. Then this function is a homomorphism. So why this is a homomorphism? So using elementary properties of determinants, we know that if I have determinant of the product of 2 matrices, then this is the same as product of the determinant of 2 matrices. So determinant of A into B is equal to determinant of A into determinant of B. So of course this determinant of A is nothing but phi of A, and determinant of B is nothing but phi of B. So we can show that phi of A into B is equal to phi of A into phi of B. So the multiplication between A and B is the matrix multiplication, and the multiplication between phi of A and phi of B is the multiplication of real numbers, because phi of A is a real number, phi of B is a real number. So this satisfies the condition of the homomorphism. So we can say that this function phi from GL to R under multiplication non-zero real numbers is a homomorphism. So a notation that we'll be using very frequently is hom G to H. So if G is a group, H is a group, then the set of all homomorphisms from G to H is denoted by hom GH. So kernel of a homomorphism, so the kernel of a homomorphism F from G to H is set of all elements. So F is a homomorphism from G to H. So it's set of all elements G belongs to capital G such that F of G is equal to identity. So in other words, we are considering all those elements of G that are mapped to the identity element of H. So our next definition is isomorphism. So once again, a very important concept when dealing with groups. So it's just like equality of groups. So for example, if we take real numbers, then of course we know that two real numbers are equal if they are representing the same number, or if they are representing the same number of quantities. So for example, 2 is equal to 2 because 2 is basically representing two quantities, and this 2 is representing the two quantities, so their number is equal. Now when we are discussing the groups, then the group is not just a set, it is basically a set with some special structure on it. So when we talk about equality of groups, then of course their structure must be same with respect to the group structure. So in other words, whenever we talk about the equality of the groups, then we talk about the term isomorphism. So isomorphism is the equality of the groups. So a map phi from G to G prime between the two groups G and G prime is isomorphism if it is bijective and if it is homomorphism. So we know what is a homomorphism, but the other condition that it needs to be satisfied is that it has to be bijective. So a function is bijective if it is one-to-one and onto function. So if these two conditions are satisfied, then we say that the function is bijective. So let's consider an example, phi from R positive. So we have seen that R is group under addition, and this R star, which is set of all positive real numbers under multiplication. So let's define this map phi of x is equal to e raised to power x. Then this phi is basically homomorphism. So this is an exercise for you to check that is phi an isomorphism. So basically you just need to check that if it is one-to-one or not, or if it is onto or not. So we can multiply two different groups to get another group. So this procedure of multiplying two groups to get another group is called external direct product. So the direct product between two groups G and H denoted by G cross H is defined with the binary operation of point-wise multiplication. So we have seen what is cross product of two sets. So we know what is G cross H because G is a set under some conditions and H is also a set under some conditions. So we can take cross product of these two sets as well. And so G cross H contains ordered pairs. So GH is one ordered pair, G prime H prime is another ordered pair. Then we can multiply these two elements of G cross H in the following way. So multiply the first ordinates and multiply the second coordinates in the following way. So similarly we can define external direct product of finitely many groups. So if we can do it for two groups, then we can also do it for finitely many groups. But if these groups GIs are commutative groups, then sometimes we denote this external direct product as external direct sum of the groups. So this is the only difference between the general term of external direct product and external direct sum of the groups. So of course we can calculate many examples. So let's consider an example. Take set of real numbers under addition and take set of integers under addition, then consider their cross product or cross z, and then we define r1 z1 multiplied with r2 z2 to be basically r1 plus r2, because the binary operation of r is addition and the binary operation of z is also addition, so z1 plus z2. So that's how we define binary operation on this cross product of r and z. So internal direct product. So let a group G have subgroups Hi, then G is internal direct product of the subgroups Hi if the map phi from H1 cross H2 up to Hn to G defined by this simple multiplication is an isomorphism. So if G is internal direct product of the subgroups Hi, then every element of G can be written uniquely as G is equal to H1, H2, Hn, where Hi belongs to capital Hi. So we will see many examples of this internal direct product in our course later on. So what is a direct sum? A group G is direct sum of two groups H1 and H2 if the subgroups H1 and H2 are normal subgroups of G, their intersection is empty and G is generated by H1 and H2, and we write G is equal to H1 direct sum H2. So once again we will see many examples of this direct sum later in our course. Finitely generated abelian groups. Let G be a group and AI belongs to capital G. So the smallest subgroup of G containing these AIs is the subgroup generated by these AIs. If this subgroup is all of G, then AIs generate G and AIs are the generators of G. If there is a finite set AI which generates G, then G is finitely generated. So before going to finitely generated abelian groups, we first discuss what is finitely generated group. So consider a group G. So if there are elements A1 up to so on, could be finite, could be infinite. So these elements contained in the group G. So the smallest subgroup of G containing all these elements. So how to obtain the smallest subgroup of G containing all these elements? So it's very simple. Take intersection of all subgroups containing these elements. So that will be the smallest subgroup of G containing all these elements. So in other words, I am just talking about take intersection of H such that this H contains, so this H contains this set AI, A1 up to AI up to so on. So set of all subgroups of G containing these elements, and then take intersection of all those subgroups, then this is the smallest subgroup containing A1 up to AN. Okay, so we are taking intersection of the subgroups and the result is also a subgroup. So this is a very simple result that I'm leaving it as an exercise. So what is the result that you need to show? So if H1, H2 are two subgroups of G, then H1 intersection H2 is also subgroup of G. So this is true So when we take intersection of all subgroups containing these elements, then of course it's going to be a subgroup of G, and this subgroup is the smallest subgroup containing all these elements. So this subgroup is generated by these elements, and if this subgroup is all of G, then we say that these elements AIs generate the group G, and AI are called the generators of the group G. So if there exists a finite set AI, or this set AI if it is finite, then we say that G is finitely generated group. So elements of subgroups of G generated by these are finite products of integral powers of AI, so where power of AI may occur several times in the product. So very simply, so the elements of the subgroup generated by these are finite products of integral powers of AI. So for example, we have A1 up to AI up to so on. So this is the generating set, or this is the set, and we are considering the subgroup of G generated by this set. So let that subgroup is H. So this H is generated by these elements. Then what are the elements of H? So the elements of H are basically products of the integral powers. So take any integer, so could be positive, could be negative. So -1, A2 raised to power -3, A10 raised to power 100, A, once again there could be a repetition as well, so A1 raised to power 10 up to so on. So these are the elements of this subgroup H, which is generated by these elements. Okay. Similarly, I can write another element, let's say A1 raised to power -10. Similarly, I can write another element, let's say A3 raised to power -7 and A1 raised to power 20. So products of the integral powers of these generators are the elements of the group H. And of course, if this set generates the whole group, then every element of the group is product of integer powers of these elements. So let's consider an example. So we know that symmetric group S3 is the group of all permutation on the set of 3 elements. So its elements can be written as, so set of all permutations. So what does 1, 2 mean? So 1, 2 is a permutation. So what is a permutation? A bijective function from the set 1, 2, 3 to the set 1, 2, 3 is basically a permutation. So what is this permutation 1, 2, for example? So basically it's a function which takes 1 to 2 and which takes 2 to 1 and which takes 3 to 3. So in other words, I can also write it in the following way: 1, 2, 3. So 1 goes to 2, 2 goes to 1, and 3 goes to 3. Similarly, we can say that what is this permutation 1, 2, 3? So basically this 1, 2, 3 permutation is this permutation which takes 1 goes to 2, 2 goes to 3, and 3 goes to 1. And similarly other permutations. So there are only 6 permutations on the set of 3 elements, and the collection of all these permutations form a group under the composition of functions, because these are functions. So now if we take x to be 1, 2 and y to be 1, 3, then the elements of S3 are given as 1x, y, y square, x into y square. So we can say that if I take the set x, y and consider the smallest subgroup of S3 containing these 2 elements, then it will be S3. So basically S3 is generated by these 2 elements. In other words, every element of S3 is product of integral powers of y. So we can see that very special integral powers in this set. But if I take any other power of x, for example x raised to power -7, y raised to power 10, then it's going to be one of these 6 elements. So we can use properties of x and properties of y to deduce that it's going to be one of these 6 elements. Similarly, we can take any other integer power of x and y, and it's always going to be one of these 6 elements. So the elements of S3 are product of integer powers of x and y. Another example is Z cross Z2 is generated by 1 0 0 1. So what is Z2? So the elements of Z2 are 0 and 1. So these are congruence classes. So if you have any integer, then divided by 2, and this set contains the remainder of that element. So in other words, this class 0 is collection of all elements which are divisible by 2. So collection of all integers 0, 2, 4, 6, could be negative as well, up to so on. So if I divide 2 by 2, then the remainder is always 0, because 2 completely divides 2. If I divide 4 by 2, then the answer is, the remainder is 0. Similarly for other elements, but what about the elements of the class 1? So it is the collection of all elements to which if I divide by 2, then the remainder will always be 1. So for example, the number 1, similarly the number 3, similarly the number 5, 7, up to so on. So these are all the elements. If I divide, for example, 5 by 2, then 2 2s are 4, and the result is 1. The remainder I can't divide further. So what is the remainder? Remainder is 1. So that's why this 5 belongs to this 1 class. So Z2 is basically 2 elements or 2 classes. If I divide by 2, then I have only 2 options. Either I will get 0 or I will get a 1. So Z2 has these 2 elements. We can also divide, we can also define addition in this set, and this set is basically under addition forms a group. Similarly, we have also discussed what is the set of integers, and the set of integers under addition forms a group. Now every element of Z cross Z2 can be written as integer powers of these 2 elements. So I'm leaving this as an exercise. So a group G is torsion if every element in G is of finite order, and G is torsion free if no element other than the identity is of finite order. So for example, if I have the group C4, which we just discussed, generated by iota, so its elements are iota minus 1, minus iota, and 1. So every element of G is of finite order. So let's see what is the order of iota. So of course iota raised to power 4 is 1, and this is the smallest power. So this is again an exercise for you to check that there is no smaller power than 4, such that iota raised to power that power is equal to 1. Similarly, we have also seen that the order of minus 1 is 2. Similarly, we can see that the order of minus iota is 4, and the order is identity, of course, is 1. So we have seen that in this group C4, every element of the group has finite order. So C4 is a torsion group. But of course there are many other groups as well where no element other than identity is of finite order. So for example, consider the set of real numbers under addition. So apart from the 0, which is the identity under this binary operation, apart from this element, no other element has finite order. So the symmetric group S3 is a torsion group. On the other hand, the group Z is torsion free. So there is another example. So in general, we can prove that, of course this is not part of our course, but we can show that every finite group is a torsion group due to the results coming from the group theory. So let's go to our next concept. So what is torsion subgroup? In an abelian group G, the set of all elements of G of finite order is a subgroup of G called the torsion subgroup of G. So for example, consider this abelian group. We have seen that Z under addition is a group. Z2, which has 2 elements 0 and 1, under addition is a group. So the torsion subgroup is this element. So apart from the identity, we have one other element of this group. So this is torsion subgroup of this group. So 0 0, of course we can see that it has finite order, but what about 0 1? So if I add 0 1 into 0 1, of course we have to add it, because in this case the binary operation is addition. So this is equal to 0 into 1 plus 1. So what is 1 plus 1? Of course we know that 1 plus 1 is 2, but this 2, where this 2 belongs to in this set. So in this set 2 belongs to this class, because if I divide 2 by 2, then the remainder is always 0. So that's why this 2 is nothing but 0. So if I add this element twice, then the result is the identity. So in other words, the order of this element is 2. So it has finite order. Similarly, 0 0 is identity element. If I add it into itself, then of course the result is the same, the identity element. So the torsion subgroup of Z cross Z2 has these two elements. So this is a very important result of finitely generated abelian group. So every finitely generated abelian group is isomorphic to a direct product of cyclic groups in the form this. So where pi are prime numbers, not necessarily distinct, and also in the form this, where mi divides mi plus 1. So in both cases the direct product is unique except for possible rearrangements of the factor. So that is the number which is the Betti number of Z, of factors of Z, is unique. So this number, so for example this is the first copy, this is the second copy, up to so on. So let's say there are r copies of Z, or r number of Z's in this direct product, then this r is called Betti number. Okay, so the torsion coefficients mi of gi are also unique, and the prime powers are also unique. So these numbers are unique, but their order could be different. So for example, it could be zp2 raised to power r2 cross zp10 raised to power r10, up to so on, but r1 or p1 raised to power r1 should be one of these copies. So the primes should be unique, but their order could be different. So very important result, the next lemma, and we'll be using it in our consequent lectures. So a finitely generated torsion-free abelian group F is isomorphic to Z cross Z cross Z for some number m of factor, and of course we have seen that this number m is called the Betti number of F. So if it is a finitely generated and abelian group and there is no torsion element, so it's torsion free, which means there is no torsion element, then it is nothing but direct product of integers. So our next concept is free groups. Let A be set of elements ai. We call a symbol of the form ai raised to power n a syllable. An array of symbols written in juxtaposition is called a word. So for example, if the set A is ABC, then a square b cube c, a in b raised to power 10 are examples of words. So in this case, a square is a syllable, b cube is a syllable, c is a syllable. We multiply these three syllables to form a word. Similarly, a is a syllable, b raised to power 10 is a syllable, and we multiply them to get a word. So next we shall see that the collection of all reduced words. So what is a reduced word? We shall define it in the following way. Okay, so from the set A, so denoted by f of A, can be made into a group. So for w1 w2 belongs to f of A, we define w1 w2 to be the reduced word of the word obtained from the following elementary contractions. So what we are trying to say is take a set A of symbols or elements, take collection of all words, and then take collection of all reduced words, and we denote that collection of reduced words by f of a. So what are we using to reduce those words? So we are using these two operations. So if there is an element ai raised to power m and multiplied it with by ai raised to power n, then it is the same as ai raised to power m plus n. And similarly replace ai raised to power 0 with 1. So after following these two operations, the collection of all words in the alphabets of A or in the symbols of A is collection of reduced words, and it is denoted by f of A. And after introducing the empty word which has no syllable, the set of reduced words under this operation just defined is a free group generated by A. Okay, so we have done many steps. So in the first step we define what is a word. So a word is a collection of this form. Secondly, we define we want to reduce the words. So how to reduce the words? So for example, if I have a word a raised to power 10, a raised to power minus 2, b a raised to power 3, b raised to power 3, b raised to power 2, c, up to so on. I can use this first rule to write down a raised to power 10 minus 2 as a raised to power 8, b, and similarly a raised to power 3, b raised to power 3 into b raised to power 2 is b raised to power 5, and c. So this is the reduced word after using the first operation. Similarly, if I have something like a raised to power 2, a raised to power 3, b raised to power 3, b raised to power minus 3, c, then I can use once again the first operation, a raised to power 5, and similarly what is b raised to power 3 minus b raised to power 3 is b raised to power 0, and c. So what is b raised to power 0? So using this second condition we can say that this is 1 into c, so this is a raised to power 5 into c. So the collection of all reduced words forms a group. So what is going to be the binary operation? So the binary operation of this collection of reduced word is just the word juxtaposition. So for example, if I need to multiply this word with this word, then I just write them down with one another. So just like this, b raised to power 5, c, a raised to power 5, c. So I have written this word and this word. So this new word is basically the multiplication of this word and this reduced word. Okay, so under this operation the set of reduced word form group. So consider another example. If a is equal to abc and fa is the group of all reduced words in the symbols abc, some of the typical elements are ab square, c cube a, etc. So the inverse of ab square c is this element. So what we have done to obtain this inverse, so basically reverse the order. So we have done two things. So reverse the order. So if it is a b square c, then start from c. So c b a, and then the second step is multiply the powers by minus 1. So after following these two operations we get inverse of a word. So let's consider another word. Let's say a cube c b raised to power 10. So in the first step, so what is going to be the inverse of w? Follow the first step, reverse their order, b c a, multiply the powers by minus 1. So the power of b was 10, so the power of b should be minus 10 in w inverse. So the power of c is 1, so the power of c should be minus 1 in w inverse. Power of a is a 3, so the power of a should be minus 3 in w inverse. So let's multiply w inverse to see if their result is identity or not. So a cube c b raised to power 10 multiplied by b raised to power minus 10 c raised to power minus 1, a raised to power minus 3. So this b raised to power 10 and this b raised to power minus 10 will cancel out each other. Basically we will be using this second step of reduction, because b raised to power 0 is basically 1 according to this rule. Similarly, in the next step we will get c raised to power 1 and c raised to power minus 1, and their product will be c raised to power 1 minus 1, which is c raised to power 0. Once again, according to this rule, it will be 1. And in the next and final step, a raised to power 3 multiplied by a raised to power minus 3, and the result will be a raised to power 0, which again by this result is 1. So the end result will be 1. Similarly, we can also show that W inverse into W is identity. So basically we have seen that if I have a collection of alphabets or collection of elements AI, then I can define syllable and then words, and then I can define what are reduced words, and then I can take collection of reduced words and define a binary operation on that set of reduced words. And that binary operation with this empty word 1 forms a group. And how to calculate inverse in that group? So we have seen an example. So under these two rules we can calculate the inverses of elements of the group generated by A. So what is a free group? So we have seen what is a group generated by a set of symbols AI. If we have a group G and a set AI, of course this set AI generates the free group generated by the set A. And if G is isomorphic to f of A under a map phi defined by phi of AI is equal to AI, then G is free on AI, and AI are the free generators of G. So as I've told you earlier, that isomorphism is nothing but the equality of groups. So if G is isomorphic to a free group, then G is free group. Okay, so a group G is free if it is free on some non-empty set AI. So the number of elements of AI is the rank of the free group. So what is a commutator subgroup? The set of all elements of a group G of the form AB, A inverse, B inverse. This generates a normal subgroup G prime of G called the commutator subgroup. So a free abelian group. So a group G is free abelian if it is isomorphic to the factor group of some free group by its commutator subgroup. So if I have a group and if I take its quotient with commutator subgroup, then basically I'm requiring that the resulting group will be a abelian group, because when I'm taking quotient of a group with some other group, then basically I'm requiring that every element of this group G prime is going to act like an identity in my new structure. So for example, the elements of the commutator group are A, B, A inverse, B inverse. So this will act like an identity in our new group. So in other words, AB is equal to BA. Okay, so in our new structure, these elements will behave like a commutator group. So in other words, we can say that this G quotient G prime is going to be an abelian group, because the elements due to which it was not abelian, so we have taken them to be identity. So we have taken care of every non-abelianness, and then we have taken quotient of this thing. So if we have a free group, and when we take quotient of this free group with the commutator subgroup, then we will get a free abelian group. So the group Z cross up to so on for M factors is a free abelian group of rank M. Finite presentation. An important concept in the group theory is finite presentation. So we can represent a group using generators and relations. So for example, group G is finitely generated if A, B, C up to so on are generators, and these are the relations of the group. So in case of S3, so we have seen that every element can be written as product of powers of X and Y. So we can say that X and Y are generators, and what are the relations satisfied by? the elements of S3 or the generators of S3 in this case. So x square is equal to y cube is equal to xy square is equal to 1. So if we use these relations, then we will get every element of S3. So of course we can write 1xy. So what about x square? Of course x square is equal to 1, so x square will not exist here. Similarly, what about x cube? So x cube is nothing but x square into x, and x square is identity, so x cube is equal to x then. So x square, x is 1 into x, which is equal to x, so x cube is x, which is already in the set, so it will not be in the set. Similarly, we can go on, and when we will write down all the possible combinations of x and y, product of powers of x and y, then we will get exactly xy square, y square, and we have seen that this is S3. So this is the final presentation of a group. So this is an example. So basically S3 is nothing but basically all the possible identity, rotation and reflections of a triangle. Okay, so we can see that set of all possible elements of such type or set of all symmetries of the triangle forms S3, and its elements are acting like this table. So if I multiply 1 into 1, then I will get 1. So this 1 basically is coming from these transformations. So our next concept is vector space. So what is a vector space? A vector space is a set X over a field R or C or any other field. So it's a vector space if it is a group, a abelian group under addition. So we can see that the first 1, 2, 3, 4 conditions make sure that this set X is a abelian group, and we have few extra conditions apart from the abelianness group. So these conditions make sure that X, the elements of X and the elements of the field behave in a way that we want them to. So there are many examples of vector spaces. So for example, R is a vector space over itself. So R over R is a vector space. Similarly, R2 over R is a vector space. Similarly, C2 over C is a vector space. Okay, so this is an exercise for you to check that these examples satisfy the axioms of the vector space. A subspace, in a very similar way we can define what is a subspace. Of course it is a subset of a vector space which is satisfying the axioms of the vector space. So for any finite set of vectors, the vector x of the form is said to be linear combination of xi's. So basically x is equal to a1 x1 plus a2 x2 up to so on plus an xn. So the set xi is said to be linearly independent. If their combination is 0, then the only possibility is that all the coefficients are 0. So for example, if we take R3, which is a vector space over R, then 1 0 0 0 1 0 and 0 0 1, these three elements are linearly independent, because if I take a linear combination of these three elements, then the result is going to be this, and if I put it equal to 0, then the resulting will be a1 a2 a3 equal to 0, which means that a1 is 0, a2 is 0 and a3 is 0. So this 0 is basically the 0 vector. So this 0 vector is 0 0 0. So two vectors are same if their corresponding coefficients are same in this case. So a1 is 0, a2 is 0 and a3 is 0. So we can say that these three elements are linearly independent. So a set of linearly independent vectors is called basis of X if every element of X can be written as a linear combination of A. So the number of elements in a basis is invariant and is called the dimension of X. So for example, if I take R3, then every element of R3 can be written as a linear combination of these three elements. So we can say that these three elements forms a basis of R3, and since there are three elements, so the dimension of R3 is 3. So of course there are many other basis elements of R3 as well. So every basis has the same number of elements, so that's why this number, which is called the dimension of the vector space, is invariant. Okay, so you can take any other basis elements as well, but their number must always be 3 in this case. So the direct sum, a direct sum of two vector spaces U and V over the same set of scalars or over the same field, denoted by U direct sum V, is a vector space defined by U direct sum V, which is basically nothing but the cross product of U and V in this case, and that's how we define the operation on these two vector spaces. So what is a convex set? So a set of vectors in a vector space X of the form is called segment from X1 to X2. So if all segments joining any two vectors of a set B of X is contained in B, then the set B is called convex set. So for example, if I take this set, then this is not a convex set, because if I take this point and the line segment joining them, of course this is contained in the set. But if I take this element and this element, then the line segment joining them is not contained in the set B, because this part is outside B. But if I take circle, then the circle is of course a convex set. Similarly, there are many other examples of convex sets. So a linear transformation on a vector space X is an operator that maps every element X to Tx such that it satisfies the following condition. So linear transformation is just like homomorphism of groups. So in case of vector spaces, we have linear transformation. So this is basically a mapping which preserves the two operations on the vector space, so scalar multiplication and addition. So what is a linear functional? So a linear functional is a scalar valued function on a vector space. So scalar valued function means if X is a vector space over, let's say, a set of real numbers, then f is a function from X to R. Similarly, if X is a vector space over any field f, then f is a function from X to f, and it satisfies the properties of a linear transformation. Okay, so we have a particular linear functional, okay, which is 0, which will give me 0 for every element of the vector space. Similarly, we can define dual space, which is the collection of all linear functionals, and this space is called the dual space. And sometimes if V is a vector space, we denote this space by V upper star. So this is the end of our today's lecture. If you are interested in studying groups and vector spaces more, then these are the references that will be helpful for your reading. So we have Algebra by Hungerford, and a first course in abstract algebra by J.B. Fraley, and linear algebra and its application by David Seeley. This is the end of the lecture. Thank you very much.